get to this page, and if you go up here where the gear is, do compatibility view settings. The website will be there if you haven't already done it, but I've already hit add, and it's already added oftc.edu. And it will remain there as long as you don't clear certain parts of your browsing history. If you do clear parts of your browsing history, that can go away. But if I don't set the compatibility mode, I'll type in the right password, right username, and it'll keep looking like I'm just not logged in correctly, and you'll be scratching your head. All right, enough of that. We are going to be covering math today. Just what everybody wants to do on a Monday morning, even me. But we'll start with these numbering systems, and we're going to go as slow or as fast as needed. When we talk about binary, we talk about hexadecimal, we talk about octal, those three. Primarily, you'll be dealing with those in the PLC world. Primarily, you'll see views in octal, you'll see views in hexadecimal. And it's good to understand how those numbers translate to what we use, which is decimal. So if we'd all been born with 12 fingers and 12 toes, we'd be using a different numbering system. We were born with 10, and that's what our number system is based off of, is a base 10. And we'll see that as we go along. I've got this wonderful clicker which works with PowerPoint, but it doesn't work with NIDA. I'll have to manually do these. So this is kind of an overview, and I'll kind of talk about how NIDA works as we go along. But NIDA will give you some objectives, and NIDA is real good about repeating material. If you're a little bit impatient though, you can go, come on, let's get this train rolling. But it does do a good job of kind of hammering in a point, but sometimes, in my opinion, it might beat a dead horse from time to time. You know, we joke about counting is easy until you run out of fingers, but that really is what our number system is based off of, and it is base 10. And once you understand how the base system works, I mean, we've grown up counting all our lives, so we take it for granted. We don't really think about how did we come up with 10, and the next number being 11, and then the number after 99 being 100, and so forth and so on. But once you really do, these other base systems are more understandable. But yeah, as we get above 10, you know, we have to start using our toes, or if we're using our fingers. But jokingly, it is because we have to shift and add another number at that point. So once we exceed 10, or 0 through 9, which is 10 positions, we have to go to 10, which adds a different number before the decimal point. And we're going to see that here in a minute. Why do you think computers don't use decimals? Can a computer see the difference between on and off? It just sees on or off, and that's digital. 1 being on, 0 being off. And that's actually where, if any of you have ever wondered, where did we get the symbol for the power button? We got this little button that looks like this right here on most of our power. That's a 0, and that's a 1. That stands for on and off. So the universal symbol for power is actually a base number, and you'll see that as we go along in binary. And that's because computers, that's typically what we use, and it's progressed into other systems too. And it's hard to talk to the camera when I have to keep doing this. But yeah, computers use binary, and we're going to talk about how to convert between all these different systems that we have. Now NIDA, once you get through kind of objective, it presents you with this screen. Now, fair warning, experiments are designed to go with a console that's only in my lab down there. So if you try to go in experiments, you're going to hit a roadblock, because after a point, the NIDA station has to talk to the computer that it's hooked up to. So obviously you're not hooked to a NIDA station. So if you try to do the experiment, it's just not going to get any further. But it'll give you this list, and let's just say you're at home and you're browsing through this, and you meant to click into number versions, but you click into math operations, and you go, man, I didn't mean math operations, I meant number. If you go ahead and hit start, once you get down here, you'll see these 3 bars down at the screen. That brings you back to the menu. So if you ever accidentally get in a lesson that you don't want to be in, click those 3 bars, click OK, and it'll take you back. So that's how you can kind of get around. Otherwise, you just have to go through slide after slide after slide. And if you exit out, it's going to lock you out for about 10 minutes. All right, so let's talk about number systems. Primarily, in digital electronics, we talked about these already, decimal, binary, octal, and hexadecimal. And they're all related, and there are some offshoots of some of these. One of the things you may hear about at some point is what we call binary coded decimal, and it's still a form of binary. It's just a way of expressing decimal numbers in binary. But those are the 4 you'll be dealing with. Decimal that we're all familiar with. Binary, which is base 2, it only uses 0 and 1s. Octal uses 0 through 7. And hexadecimal uses 0 through F. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So 0 through F. It's kind of like when you go, anybody ever went to a store and bought a pinochle deck of cards by mistake? You know, they don't have the same cards in it. Same thing happens here. You end up with numbers being a little wonky looking when you get into it. But once you really understand, not so bad. And you'll see some more of this as we go through. There's just no way to advance. I have to actually click on the right key. All right, and like I said, we use decimal every day. And the base numbers we use are 0 through 9, just as I talked about. And if we grow to a larger number, we have to have more than one number there. And this is a perfect example. When we start looking at decimal numbers, this is the 1's placeholder, and this is the 10. Once we exceed 9, we have to move over and add another number, and that number increases the value by 10. So basically, whatever we have here, when we multiply by 1, whatever we have here, we multiply by 10, we add them together. And because we already know this system, it's automatic. I mean, you know, we don't say 3 times 10 is 30, 9 times 1 is 9, so that's 39. We already know that. Man, that's the one we work off of. But when we get to these other systems, that's exactly what we're going to have to do. We're going to have to understand what those placeholders mean. We're going to have to do the math and understand it that way. And I'll get to find another way to study. All right. So once we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we're out of fingers. So then we have to go back to 0, but then we add another decimal or another number to the left of the decimal, to the left of the 1's position, which is the 10. And that's where we get 10. And we can count all the way up to 99. And then once we hit 99, we have to have a hundreds column. We'll put a 1 there, and so forth and so on. So as these numbers grow, we're actually adding a column that is a value of 10-fold. So 0, 10, 100, 1,000, 10,000, so forth and so on. So it's just increasing by a factor of 10 each time. And this is just a visual example. You know, 1 times 10 is 10, 10 times 10 is 100, 100 times 10, and 1,000 times 10 gives us the 1,000 and 10,000 we see there. So again, something we're already used to, but if we understand how those columns work and how those numbers in that column represent a value, then it's going to help us understand these other base numbers too. All right, and NIDA will test you all along, and it'll give you feedback. If I say, what is the decimal number if the count is increased by 1? If I click on the wrong one, it'll feedback to me. If I can find my mouse. There it is. So if I click on 100, it'll say incorrect, try again. When I click on the correct one, it'll tell me. So the good thing is it'll kind of feedback as it goes along. So we really understand tens because, hey, that's what we've used every day since, you know, we were that high. But let's talk about binary now. uses 2 digits, 0 and 1. And that's because just like with 10, once we hit 9, we have to increment up. Once we go from 0 to 1, there isn't a number higher, so we have to add another digit, and that number becomes 1, 0. Then we add 1 to that, it becomes 1, 1. Then we add 1 to it. We keep counting, and you'll see that here in a moment. So obviously, you know, each of the 2 digits is written in the 1 column. So the number in binary, and I apologize for those of you that are on the other side of the room, but I gotta pick a board. So anytime you need to scoot this way. So it's still math, and it's still math that works like it does. If we have 0 and we have 1, and then we increase that value, we go to 1, 0, and if we add 1 to that, we go to 1, 1. If we add 1 to this becomes a 0, this becomes a 0, then we have 100. Then we would have 101, 110, 111, and then we increase to 1000. So all it is we're just shifting placeholders, just like we do in decimal. We're just doing a whole heck of a lot faster because it's binary. We only use 2 numbers. And you'll see that a little more as this comes to play. So once that 1's column, if we go from 0 to 1, and then we add one more 1, that new 1 now goes into the 2's column, and the 1 becomes a 0, because in binary, 10 or 1 plus 1 is not equal to 2, it's equal to 10 if you want to express it in decimal form. I prefer to say 1, 0, because that keeps us from being confused between 10 in decimal and 1, 0 in binary, even though on paper they look the same, but they don't hold the same value. And the reason we're using binary, again, computers can't see in between, they can't see large numbers. They either know you're sending it a high signal, which is a 1, or a low signal, which is a 0. So I could, in binary, there's a way to express my name, Lee Radney, and that would be a bunch of 1s and 0s back to back to back to back that represent a binary form of Lee Radney. And so that's what a computer has to use, because it can't see a value in between. It sees either on or off, which is high or low. Now, just like the 10's column logo, when we went across, binary has the same deal, except it's a factor of 2. With decimal, it was 1s, 10s, 100s, and so forth. With binary, and I won't write 1s, I'll just write 1, 2, 4, 8, 16, 32, and so forth. So these placeholders represent a number to us as far as a decimal number, but they're going in factors of 2, whereas decimal goes in factors of 10. So we're shifting the columns based on the base. So a while ago, the base was 10, 1, 10, 100, 1,000, 10,000, so forth. Here, the base is 2, so 1, 2, 4, 8, 16. So still the same premise, just with a much smaller base. So what happens if we increase this number by 1? What's our value? Say it? 1, 0, that's right. Just like we talked about before, we're already maxed out in the 1's column. If we add a 1 to that, that becomes a 0, and then we shift the 1 over to the next column. So that's exactly right. All right. So let's do a few, before we move into binary, we're going to get a chance to review it. But let's do a few numbers in binary just to make sure we can add and subtract, or not add, add, not subtract. We'll get to subtraction later. But let's say we have 1, 1, 0 plus 1, 0. Switch to binary mode, not decimal mode. But what is 0 and 0? 0. What is 1 and 1 in binary? 0. And carry what? 1 and 1. What's 1 and 1 in binary? And carry a 1. So 110 plus 10 in binary is 1,000. Now let's see if mathematically that works out. We started out with 1, 1, 0. And the way we can convert that to a decimal number is just add the columns. Nothing here, a 2 and a 4. So what we're adding in binary, in decimal, is 6. And then we have plus 1, 0, which is right here, which is 2. And of course that's 8. And we said that equals 1,000. And again, we add the numbers. 8 plus nothing plus nothing plus nothing equals 8. So we're able to see that as long as we can carry those 1s and those 0s in a way that binary wants us to carry them, which means just like in decimal, we can't get above a 9 without having to carry. In binary, we can't get above a 1 without having to carry. So the same rules apply, just a different base. So I'll let that marinate a minute, then we're going to go to octal. Now, computers, how many of you have ever heard of 8-bit architecture, 16-bit architecture, 32-bit architecture, 64-bit? Any of you ever heard that phraseology? Well, even 8-bit binary values can become a little confusing, but especially a 64-bit binary number, if you're trying to view it and really understand what it is, and I'm not going to go all the way out to 64 bits, but imagine trying to look at a number like this right here. And go, oh, that equals blah. I couldn't tell you, we're probably at about 14 or 15 there, but imagine a 64-bit live number. It gets big. And of course, the reason we have these bit architectures, the faster we can exchange numbers, send numbers through a computer, the faster we're going to process data. And anybody that's ever used a slow computer, we all want faster. So when the first computers came out, they were 8 bits, and we moved to 16, 32, 64, and maybe beyond that. I've got out of the geekdom of the raw end, but I have heard of 64-bit architecture, so it'll double every so often. Now again, binary, octal, just like binary, has a set base, just like decimal. 0 through 10 for decimal, 0 through 1 for binary, 0 through 7 for octal. So that's the name octal, 8 positions, octopus, octal, octo being the prefix. And again, the same thing happens. We can count 0 through 7, but once we hit 7, we've exhausted the values that are in octal. So we have to take a 1 over to the next position. Now notice that position, just like decimal was a factor of 10, binary was a factor of 2, octal, no surprise, is a factor of 8. So if we look at octal, compared to decimal, compared to binary, in decimal, we had 1s, 10, 100, 1,000. Binary, we had 1, Mark, we're about to give out 1, 2, 4, 8. In octal, we have 1, 8, 16, and 128. No, 1864. I was so wanting to do easy math in my head this morning when it didn't work out. 1864 and 256.
Why wouldn't it be 1832 and 64?
Well, it increases by, you multiply each column by 8. So here we multiply each column by 10. 1, 10, 1,000, 100, 1,000. Here we multiply each column by 2. 2, 4, 8. here, 8 times 8 is 64, 8 times 64 is 1956, is it? Y'all forgive me, math is 512. Said if we kept on, it would be 4,096, another factor of 8, 32,768. And I'm not gonna press you anymore after that, because it's way too early. But yeah, we just factor by 10 in decimal, 1 times 10, 10 times 10, 100 times 10, 1,000 times 10. Same way here, 8 times 8, 64 times 8, 512 times 8, so forth. So. So again, once we get past 7, we have to have a carryover, and that becomes a 1 in the 8's column here. And we see that. Should have went to this slide before I started writing the numbers down. I'm telling you. So again, we shift over. So again, these numbers represent a value, just like they do in tens, just like they do in binary, but in this case, it's an octal value. And we can do the math the same way here. So what's our next number once we hit 77? 100. A lot of people like to choose 80 there. But yeah, 100, because there is no 8. If you see an 8 in a number, it's not octal. Could be hexadecimal, it could be decimal. But if you ever see an 8, it's definitely not octal. So 100 is the correct answer. All right, so let's talk about hexadecimal. So somebody said the devil got in math when we started adding letters in algebra. Well, we've just added letters to the number system. So hexadecimal, rather than using 0 through 9, somebody somewhere said, hey, let's throw A through F and count all the way to 16. And that's what we did. And it was good or bad, depending on your perspective. But if you notice, each one of these bases that we're dealing with in computers, notice, outside of decimal, let's take away decimal, let's talk about binary. Binary is 2, octal is 8, hexadecimal is 16. If you notice, they all can be factored into one another. I can going by values of 8 other than binary, which is 2. So hexadecimal and octal are both divisible by 8, and there's a reason we use both of them. And octal was used more in an 8-bit. Hexadecimal was used more in a 16-bit architecture. Oh, that's the other thing while I'm thinking about it. NIDA is infamous for freezing. So if you're at home studying, you hit the next arrow, and it just kind of hangs there, you'll get you a cup of coffee, a glass of sweet tea, or some orange juice or something. It'll be back. Just have to wait on it. Check something real quick. Okay, so obviously we can count all the way up to F. A 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and remain in hexadecimal. But once we hit F, we've maxed out on our numbers, and we have to have a carry into the 16s position. And there it is. So obviously we're one number higher now than F. We're F plus 1, for lack of a better term, and we represent that by 1, 0. And this is just kind of showing you that 16 is in the times 1 equals 16, so forth and so on. We're just incrementing up by 16 by a base of 16. All right, we've got 9F in our column. We add 1 to it. What do we come up with? 9F. 9F. 100. How can we possibly come up with 100, you might ask? Yep. We have 9F plus 1. Well, we know that the 1 takes us beyond the F, so we can't add it, but that becomes a 0. We carry 1 here. 9 plus 1 and everything else we'd have it carried, but no, it isn't 100. It's A. It's A0. So it's easy to get confused when you're in between these systems, but because 9 plus 1 equals 8, then it's A0. Now we're going to see that in a minute, I promise. This is going to become a little more. So here's a good chart. Decimal, 1, 10, 100. Keep going, 1,000, 10,000, 100,000. Binary, 1, 2, 4, 8, 16, 32, 64, 128, 256, 5, 12,000, 24, 2,048, so on. You're not getting that much in these two. Octal, 1, 8, 64, 5, 12, 4,096. This one's 1, 16, 256, and I'm not going to try to do the rest of that math. 49.
36.
So the higher the number, like hexadecimal is the only one that beats decimal because we can get 16 in a column. But everything else will have more numbers when compared to decimal than we do in its decimal value. We're fixing to see some more, so that's not your only thing. We're fixing to dig a little deeper in these. Always read these summaries. They're good. Sometimes there's some information in these summaries that help you. But our decimal system uses 10 digits, 0 through 9. Binary uses 2, 0, and 1. Octal uses 8, 0 through 7. And good old hexadecimal, 0 through F. And once I get through, I have to go back to the menu. Now there are some final quizzes in here. I would, as a student, I would take those final quizzes. They're good practice. They're a little bit different each time as we go through. But there's no grade going to be given to you for those. So those are on you for your own benefit. Feel free to take those numbers, those questions as many times as you have patience. All right. Let me check the time. Make sure. Oh, yeah. All right. So the decimal equivalent to 0 is 0, 0, 0. The decimal equivalent to 1 is 0, 0, 1, 2 is 0, 1, 0, 3 is 0, 1, 1, and 4 is 100. And that's why I said there are 0, 1, 0 types of people in this world. Those who understand binary and those who don't. So try it on your friends. Oh, somebody's getting their hair cut or something like that. We've become a full service organization, so who knows? All right. At base 10, when the count reaches 9, a placeholder is put in the ones column, which is 0, and the count starts again in the tens column, and we move forth and on. So, 0 through 9, then 10, 11, all the way through 19, then that number shifts to 2, 0, 3, 0, 4, 0, all the way up to when we get to 9, 9, where we have to add another column, the 1, 0, 0 column. So again, we're shifting by values of 10. In binary, when the count reaches 1, a placeholder of 0, and then we move into the next column. And we have to keep repeating that process for multiple columns. So as we talked about over here, I forgot I can draw on this now. They got it fixed, so I could have been helping y'all a little bit by being in the middle. If I have a number that's, okay, everything but night, I spoke too soon. Callie, it worked the other day. He saw it, so I'm not just delusional. At least not today.
It worked. It came on the computer, but it didn't come on.
Oh, it comes on the computer. That's a perfect place for it to come on. Everybody can see that from there, can't they? I wonder if I can expand that, and I wonder what's going to happen. Anyway, we'll move experiment on non-class time. And so forth. So I would literally count 0 would be my first number. Then it would be 1. Then it would be 1, 0. Then it would be 1, 1. Then it would be 1, 0, 0. Then it would be 1, 0, 1. Then it would be 1, 1, 0. Then it would be 1, 1, 1. And if we look at that, we really added 1 each time. 0 plus 1 equals 1. If we add 1 here, we carry that 1 down, keep this 1. If we add 1 to 1, that gives us 0. If we add 1 to that 1, that gives us 0. If we bring that 1 over here, we have 100. And if we add 1 to 1, 0, 0, we just do the 1 and just lather, rinse, repeat throughout the rest of the process. So literally, we're shifting those placeholders as if we're getting to 9 in decimal, but once we get to 1 in binary, we have to bring that, have to write a 0 and bring it over to the next column. So we're doing the same thing, it's just messing with our mind a little bit. So there's the difference. In decimal, you know, we have 1s, 10s, 1000. It's not literally meaning those numbers match. It just means we're adding a placeholder. And when we put a 1 in binary here, that represents 2. When we put a 1 in decimal, that represents 10. So that's the difference. But we do count 0 through 9 in the decimal side of things. Did I give up? Sure.
No,
Okay. All right. So binary is the same way, just like before in the decimal system. If we have 439, we don't manually in our heads go, well, 4 times 100 is 400, and 3 times 10 is 30, and 9 times 1 is 9. So let's say that's 400 plus 30 plus 9, and get 439. But we can in binary. In fact, it's going to help us out if we can do that. But the reason is we already understand, and if we all talked in binary, we'd be handling decimal in the same manner. So it's the difference there. So I'm going to take and write some numbers here. And we're going to take a minute. I'm going to add a few more columns. We're going to do some decimal math from a binary perspective. So if I write this number, I use a different color so it doesn't blend with the lines. If I write the number 1, 0, 0, 1, 1, 0, 1, 1, I can look at that in decimal and tell you, I'd have to put some commas in there. But in binary, I can't tell you what it is readily without using this trick we're about to use. And that's, we look at each column. If there's a 1 there, we write its value. So 128 plus 16 plus 8 plus 2 and 1. And we can cheat. We can say 2 and 1 is 3, or we could write 2 and 1. So, if you want to shortcut it, you can go ahead and be adding a few of them up. But 128 plus 16 is 138, 144, 152, 154, 155. That is the binary equivalent to the decimal number 155. And again, we just took the values of each column that had a 1 in it. Right there. So you'll start to see some patterns, particularly if we go all 1s. And that'll always hold true, just like if we go all the way up to 9, that's one less than 10, which is our next column. It'll always be one less than the next column. So if I go here, that's 31. If I go here, that's 63. If I go here, that's 127, and so forth and so on. Because if I add all these up, I'll come one less than whatever my next column is. And if I added 1 to them, I would have just a 1 here and zeros the rest of the way. So just like in tens, when we talk about tens, if we have a column, we have 1, 10, 100, 1,000. It's the same way. 9, 9, 9 is exactly 1 less than my next column. So, share some characteristics with decimal with the way we add and subtract. All right, so let's convert the decimal to binary. So we've got decimal 21. We know it's not binary if it's 21. We've got decimal 21. It's telling us. So can we have a 1 under 32 to get decimal 21? No, because that's more than 21. We have to use the 16, so we put a 1 there. Can we put an 8, 1 under an 8? No, because 16 and 8 is 24. So that would give us too much. So now we're at 1, 0. All right, can we put a 1 under 4? Yeah, that gives us 20. And we know we need 1 more. So it's literally 1, 0, 1, 0, 1. So I'll draw that out for you. See if I can do it on the board here. Be nice. We'll let So we'll do a few more numbers now that we've got the more raised. All right, so let's take the decimal number 20. Oh, no, I can't write. Perfect.
No.
Oh, it's right over here again. Perfect.
Really?
It's bringing up another.
Yeah, that's special. We won't talk about high special. Let's work another example. Let's say we wanted decimal number 37. What do we have to put under 32? 1. How about 16? 0, because that would be 48 if we had a 1 there. So we got 32. How about under here? No, because 32 and 8 is 40, so that's still greater than 37. So how about under the 4? So that would get us to 36, right? 1, 0, 0, 1, 0, 1. So that would be 37. So you're already writing in binary. Very good. All right, so it's going to show us find the largest that doesn't exceed the number. So the largest that doesn't exceed the number for 21 would be 16. Anything greater, we can't put a 1 there. That leaves us with 5. At that point, I'm pretty well in. If I've got 5 left, I know I can put 1 under 4 and 1 under 1, and I'm done. So at that point, I already get it, but it's going to take us through the rest of them as soon as I find them. Here we go. So it's going to say 5 minus 4, which is where we put the next one equals 1, and that's where we'll put the last one, because 1 is equal to 1. There we go. Bob's drum. All right, your turn. 53. How many under the 64? None. 0. How many under the 32? 1. How many under the 16? That's 48. How many under the 8? None. How many under the 4? 1. How many under the 2? 0. How many under the 1? All right, so let's see if we did it. 1, 2, 4, 8, 16, 32. 32 and 16 is 48. 48 and 4 is 52. 52 and 1 is 52. So it's 0, 1, 1, 0, 1, 0, 1. Now you can take that front 0 off, it means nothing. It would be the same in decimal as writing this right here, which is not incorrect. But if I need to borrow $100, I could express that as 000, comma 001 dollars. But these front zeros mean nothing because they're multiplying by nothing. So just like here, we had 0110, we can get rid of that and ultimately end up with 110101. And that's what this is showing us. Those front decimals mean nothing to us other than placeholders. Right. All right. So converting a binary number using the number line is very simple. Add the values, add it up. There you go. So 100 is equal to 36. We got a 1 in the 32's column, a 1 in the 4, 32 and 4, 36. All right. So, and that's taking you through the same thing. All right. What are we there? That's 15. We did that by adding 8 plus 4 plus 2 plus 1. All right. And I think we'll pause getting in the octal. Take a 10-minute break because it's a wonderful time in the morning anyway. And we'll come back. Okay, so we're going to talk about how decimal, binary, and especially binary and octal relate. So we're going to start with 439 decimal. 439 decimal. I'm going to abbreviate that. I'm going to make some binary rows. So this is my ones, 2, 4, 8, 16, 32, 64, 128, 6. I know I don't have to add the next column simply because the next one will be 512, so we don't have to worry about a 1 being there. So for 439, obviously we are going to have a 1 here, and I'll use red so we can differentiate those lines from the black lines that separate. So that's 256. Now the question is, do we need to add 1 under 128? So if we subtract 439 minus 256, we're going to get greater than 128, I'm pretty sure, unless I really can't math this morning. So 256 plus 128 is 384. So we're at 384 now, so we can subtract 384 from 439. 9 minus 4 is 5, 13 minus 8 is 5, and 3 minus 3 is 0. So we need to form 55 now. Well, there's 64. 32 and 16 is 48 of that 55. So we need 7 more. Oh, I didn't need it there, and I read it. Okay. So again, we had 256 and 128 that created 34. We had 55 left, and as you pointed out, I wrote a 1 there, even though I meant to write a 0. 32 and 16 give us 48, which leaves 7. So if we go ahead and calculate 7 and come back and write our 0, we have a binary number now that looks like this. And all we did was basically take 439 and segment it up into the sections under the binary here until we came up with the exact value of 439. So we come up with this neat binary number of 1, 1, 0, 1, 1, 0, 1, 1, 1. What does it tell us the octal equivalent of that is? 667. You notice I used some interesting spacing. I did them in sets of 3. If I come here and I write 4, 2, 1, 4, 2, 1, 4, 2, 1, 4 plus 2 plus 1, 4 plus 2, 4 4 plus 2, that's octal. I can take the binary equivalent of a number divided into 3 columns, convert those columns to decimal, and I've got my octal back. Ain't it pretty? So we're gonna pick another number after this one, once y'all get that one right now. We're gonna do the same thing. And it doesn't matter if that number goes on bigger and bigger, we just gotta start at the right-hand side, divide it up by 3, and get our number. So I'll use a different binary number now. We'll take, we'll go ahead and add a 512 column here just for fun of it. So we're gonna convert, let's do 667 decimal, since we just had it in octal. We'll see the difference there. All right, so if I'm going to be writing the binary equivalent of 60 to 67, 1 or 0? 1. How about under 256? 0. How about under the 128? 512 plus 100, 612 plus 28 is 640. So yes, right? All right, so what we started with is we've got 512 now, plus 128. That gives us 40, 500, 640. So now we need 17 more. I can pretty well do that in my head. 27 more. I can almost do that in my head. So that's 16 plus 4 plus 0 plus 1 plus 1. So let's go back and let's add our numbers, because always in math, if you can double check, it's not a bad thing. So we're adding 512 plus 128 gives us 640, right? 640, 656, 664, 666, ooh, and 1 is 667. So this is our binary equivalent of that same number. So let's come out here and let's do one, we'll have to count the other way. 1, 1, 0, leave a space, 1, 1, 0, 1, 1, 0, 1, 1, 0. So 1, 1, 0, 1, 1, 0, 0, 1, 0. 1, 1, 0, 0, 1, okay. Right. Then 1. Okay, I knew there was a number that should be there. And these are really zeros, and we can write them, but we don't have to. Now we've got the same imaginary column set that we used before. And we can do the 1, 2, 4, 1, 2, 4, 1, 2, 4, 1, 2, 4. 4, 2 and 1. 3. 2 and 1. 2 and nothing. And 1. So, octal, octal 667, no, still saying it wrong, right? Decimal 667 is equal to octal 1233. If I math right. Seems like too much of a disparity though, something doesn't seem right there. Is that right? Or is it just too early for me? Let's consult something later. Just to be sure. So we did decimal 1, 2, 3, 3, right? What we arrived at? Wrong way. with octal,
333.
1, 2, 3, 3.
And that's C67 decimal.
Okay, it is. For some reason, my mind won't wrap myself around that, so that is correct. So, I made one mistake today, and I was thinking I had made a mistake. Good figure. Okay, so we kind of see that when we talk about decimal and how it relates to binary, that binary and octal have an interrelationship. So if we can go between decimal to binary, we can take that binary and we can convert it to octal. So our easiest means, in my opinion, of getting to octal is to take that decimal number and make it a binary, divide those binary columns into sets of 3s, and then converting that into the number. Works like fun.
Yeah.
Unlike this smart board. So it's going to show us that same thing. We just went through 667. All right, so here we've done the same thing. We divided that binary number into groups of 3s. What is it in octal? 547. 101 is 4, 2, and 1 in the column, so that would be 5. And then 104, that would be 4, and then 104, 2, and 1 column, which would give us 7. So 527. So let's look at that one more time. We basically took that long binary number, which was 101, 100, 111, 101, 100, 111. And we did 1, 2, 4, 1, 2, 4, 1, 2, 4. That's 5, 4, 7, 5. So, since we're such geniuses, now let's write it up here on this chart. 1, 1, 1, 0, 0, 1, 1, 0, 1. And let's convert it to decimal just for fun. So it'd be 256 plus 64, which would be 320. Yep, 320. Plus 32 would be 352, 356, 358, 359. 359. Good decimal. Did I math right? All right. Yeah. So back to this one was 547. Okay, all right. All right. Octal equivalent on this one. Before anybody shouts the answer out, let's each take a moment and try to work that one out. What's our first step? Divide it into 3 columns, starting from the right-hand side, move over 3 numbers, draw a line, move over 3 more, draw a line, move over 3 more, draw a line. I can tell you what it is just by doing that imaginarily, because there's only one answer up there that fits. So sometimes you get lucky and don't have to do the full math on that problem you did. And after a little while, you'll get to where these binary numbers, because you work so much in binary, you'll be able to recognize, pretty quickly in your head what a 6 versus a 7, 0, 1, 1 versus 1, 1, 1 looks like. It is the bottom. So if we start on the right-hand side, move over 3, we get 1, 1, 1. 4, 2, 1 is 7. Move over 3 more, we get 0, 0, 0. That's a 0. Move over 3 more, we get 4, 2, and 1, which is 7. Move over 1 more, because there's only, or move over to the last column, there's only 1. And that's how I knew which answer it was, because I had to begin with a 1, so it couldn't be the other 2. So it is indeed 1797. I'm gonna try something to screw up the world for just a minute. Hopefully it'll get, we can use this whiteboard. We'll fold these this way. so I can see over here what I'm doing. Yay, at least the world is even now. All right, so let's get back to the slide. Converting an octal number to its binary is the same as if we use the reverse. So just like we took the 101 and converted it to a 5, we can work the other way. We can take that 5 and convert it to 101. We can take that 3, convert it to a 011, and we can take that 4 and convert it to 101. So going back and forth between octal and binary should be pretty much a no-brainer for us. And we're going to find out if it is or not in just a minute. All right. Now it's asking what the decimal equivalent of 435 octal is. So I'm going to give you each a minute, kind of go over that. I'm going to set my whiteboard just by checking. Aha! The world is finally lining up. Uh-oh.
No, we turned to this one.
We are turning.
435?
Yeah, 435 binary and 100. It's kind of helping you out a little bit there. It's actually taking a step away from you. So don't shout it out when you get done. This will just be kind of a self-examination. Give you just a few more seconds here, and then we're on. I should do it. Let's see if we're all upon the same page here. Still see a few pins down as always. Meanwhile, for the rest of you, went to the doctor over the weekend. He said I need to watch my sodium, but I always take what he says with a grain of salt. All right. All right, so we've been handed 435 in octal, and we see this is its binary representation, which is 4, and right here, 3, 1, and 2, and 5, which is 1 and 4. So we've got half the equation there. So if we work from the right-hand side, all we got to do is add the binary up. This is the 1, 2, 4. So we got 1 and the 1. We got 1 and the 4. 1, 2, 4, 8, 16. 1, 2, 4, 8, 16, 32, 64, 128, 256. So now it's just a matter of doing the math. 256, 266, 272, 280, 285. So, and all we did was, I didn't do it on paper, but literally I had 1, 2, 4, 8, 16, 32 all the way across, and just added those numbers, just like we did a moment ago. Totaled them all up, and we got 285. Everybody understand what we did there? Don't mind going over it.
You try that again with a green marker,
I
or the
will.
black one?
Let's just do an experiment. Okay, green's not good. Blue probably won't be good. Yeah, I kind of figured that. Yeah, I think black's probably our best bet. Obviously not, I didn't make this to the Russes on the smartboards. But again, we had 1, 0, 0, 0, 1, 1, 1, 0, 1.
Go back to red.
Okay.
Red's best.
So this is our 1s, this is our 2s, this is our 4s, 8, 16, 32, 64, 128, 256. And we just added the columns that had a 1 in them. So we said 256 plus 16 plus 8 plus 4 plus 1. 256 plus 16 is 272. 280 plus 5 is 285. How many of you have ever heard of Louis Grizzard? Every time I hear the number 285, I think about the SC. He said if a bomb was ever dropped on Atlanta, He said that for, people that lived north of I-20 needed to go 75 north, people that lived south of I-20 needed to go south on 75, and all the Yankees that lived in Atlanta needed to take 285.
Nice.
Which for those of you who don't know, just circles Atlanta. Never goes anywhere. So 285 is our answer. All right, so now we're going to do hexadecimal. Because we 100% have binary, 100% have octal, 100% have decimal. So now we're going to move on to hexadecimal. So we've got 452 decimal. Binary is not that hard. Let's see how they got the binary number. We've got, and I'll use red again, 1, 1, 1. Let me write these a little further apart so I can. Oh, nice.
Oh, no.
So we'll write 1, 1, 1. 0, 0, 0, 1, 0, 0. So this is our ones, this is our twos, this is our fours, 8, 16, 32, 64, 128, and 256. So again, we can add them up by writing the values in each one that has a 1. 2, 5, 6, plus 1, 2, 8, plus 64, plus 4. So 6 and 8 is 14, 22, 2 and 5, 7, 9, 5, 2 and 5, 7, 9, 15, 452. So again, taking the binary columns, adding up all the positions that had a 1 in them to arrive at the decimal equivalent. But oh boy, hexadecimal. Yay. Hexadecimal is going to end up being just like octal, except what's the difference, you think? It's going to be 4 columns wide. So let's divide this number up into 4 columns. Go ahead and make a line, so it's kind of hard to see on there. All right, so hexadecimal, octal uses 3, because 1, 2, and 4 happen to equal 7, right? 1, 2, 4, and 8 happen to equal 15, which are the same number of places there are in hexadecimal. So we've got a 4. 1, 2, 4. So here's hexadecimal. Add up, well, we won't use that marker. Add up the marker, add up the numbers under here. All right, we've got, if we go back, we'll have to change these because remember we're dividing it in 3 columns. So this becomes 1, 2, 4, 8, 1, and we just keep repeating that process down. So we got a 4 here. Well, 8 and 4 is 12. What is the hexadecimal value for 12? C. Yes. What is the hexadecimal for 1? 1. So if you're wondering how we got hexadecimal 12 to equal C, let me run down through. 0 equals 0, 1 equals 1, all the way down to 9 equals 9. So we're tit for tat, 0 through 9 in the hexadecimal world. So this is decimal, this is hexadecimal. But normally we can get the 10, here we get the A. 11 equals B, 12 equals C, 13 equals D, 14 equals E, and 15 equals F. So that's how we got C, because we were here. So octal, divided in 3 columns, 1, 2, 4, 1, 2, 4, 1, 2, 4. Hexadecimal, divided into 4 columns, starting from the rightmost number, 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8, so on and so forth. So So we can take that root binary number. So how do we convert from decimal to binary? We just simply subtract the number. We start with the number, put a 1 in the column that it most represents. For instance, if we're trying to convert binary 47, we wouldn't have a 1 in the 64 column, but we would have a 1 in the 32. Then we'd have to subtract 32 from 47, and then we'd have to just keep working our way down. Once we get that binary number, it's a piece of cake going to octal and hexadecimal. It's just a matter of taking that binary number, dividing it into 3 columns, or dividing it into 4 columns. We could do the same thing here. If we divided it by 3, we'll try to make this line bold. 1, 2, 3. 1, 2, 3. So now we could actually take the octal equivalent of that, which would be 4, 0, and 7, right? So there's our octal. We just took and divided it into 3 columns instead of 4, and we're able to represent that as an octal number. So if we can get the binary, it should be a piece of cake doing octal and hexadecimal. So let's do a few of those. If my wife will actually cooperate. We're going to find out. Okay, it does. All right, so let's start with this number: 0, 1, 0, 1, 1, 0, 1, 1, 1, 0. All right, this is independent study for a moment. I need the binary. I need the octal. And I need the hex. Hex being short for hexadecimal.
You just run your.
Oh, did I? I mean decimal. Hey, I gave you an easy one there. You had to go and pull up the entire class. I'm just kidding. I did mean to put decimal. Good intention and all that good stuff. We'll give you a few minutes to work through that. Meanwhile, I'm going to be working at this yellow piece. that math wrong.
Yeah.
Yep, I did math wrong. Go ahead, right? Man, I'm gonna have to break out the calculator, I can tell.
What I'm doing.
I might be wrong.
That's the third time in my back where I was? Okay.
That's what I got.
Yeah, they gave me unsweet tea. I'm blaspheming Burger King.
Well, that's all right. Longhorn the other night gave me sweet tea, so.
Well, see, there's an entire problem with unsweet tea. It can't be unsweet.
It's
tea.
unsweet?
It's non-sweetened tea. Because if it was unsweetened tea, that would mean it was sweetened at one time, and they removed the sweetener.
Technically, that is true.
It's non-sweet. Unless you hear the words nine, give me sweet tea.
Yeah. Ways to stay at the head, drive myself crazy.
That's about it before we ride. Well. That's
So you know how to get it. Well, no, I've been had this. Get by there now.
All right, let's talk about how we first did it in binary to decimal, and then we'll talk about how we took that same binary and got it into octal and hex. But we'll work a few more, because this is what you need to understand. All right, so what I did was, I just added these numbers. I added 256 plus 64 plus 32 plus 8 plus 4 plus 2. So 256 and 64 give us 320. 320 plus 32 gives us 352, 360, 364, 366. So again, I just took that binary number, represented what each column's value is, 1, 2, 4, 8, 16, 32 across, and I got 366 decimal. So that comes up to here. Now, after that, it's just a matter of redistributing these things into columns of 3. So starting on the rightmost side, 0, 1, 1, 1, 0, 1, 1, 0, 1. And I don't have to worry about that leading 0 because it has no value. All right, again, this is a repeating 1, 2, 4, 1, 2, 4, 1, 2, 4. So 6, 5, and 5. So then we did the same thing for hexadecimal, except we divided it into groups of 4. So we've got 0, 1, 1, 1, 0, 1, 1, 0, and then a 1, right? So these are my columns. And we repeat 1, 2, 4, 8, 1, 2, 4, 8, 1, and there is no other numbers. This automatically becomes a 1 just because that's the only one there. 4 and 2 gives us a 6. And 8, 4, and 2 give us 14, which if we go back to our chart, or we can count it down or count it up, we know F is 15, so if we drop back 1, E would be 14. That would give us 16E. Let's do another. Sure. That was a smart word. What time is it? 9:41. All right, we got a little bit of time to work through a few more of this. Well, I've got to go check with my counterpart, see how much behind or ahead we are. All right, somebody call me out some ones and zeros.
1, 0, 1, 1, 0, 1, 1, 1.
1, 1, 1, right? All right, so I need decimal. Right over here a little bit more. I need decimal. I need octal. I need hex. I'm gonna write it under since I didn't make enough room up there. Keep it where Paul's at. Kind of work around that, some of you are still working. We'll do this more and then we'll take a break. All right, so decimal, what's our first step? Adding it up, so we gotta do the 1, 2, 4, 8, 16, unless we just really got it in our head. For numbers even this big, I pretty much, if I can do 4 digits in my head, but much more than that, I need to put it on paper. So I've got 128 plus 32, which gives me 160, plus 16 is 176, 180, 182, 183. So basically I just added up the values of my ones column with the 1, 2, 4, 8, 16 there, got my decimal equivalent. Now with octal, we said we could divvy it up into threes. So we got 1, 1, 1, 0, 1, 1, 0, 1. And again, this is just a repeating 1, 2, 4, 1, 2, 4, 1, 2, and we have 4 there. So now it's just a matter of converting those. 4, 2, and 1 is 7, 4 and 2 are 6, and 2 and 2 is just 2. So 267. Break it up into threes, get the binary representations for each of those columns. 1, 2, 4, 1, 2, 4, 1, 2, 4. That's decimal. Break it into fours. 1, 1, 1, 0, 1, 1, 0, 1. And that's a repeating 1, 2, 4, 8. 1, 2, 4, 8. 4 plus 2 plus 1, 7. 1 plus 2 plus 8 is 11. 9 is equal to 9. 10 is equal to A. Therefore, 11 is equal to B. B7. Bingo. Sorry. One more, then break time. Y'all are seeming confident now. I can feel the confidence exuding or something. You know. 0, 1, 1, 1, 0, 0, 0, 1, 1, 0, 1. I need decimal. I need octal. I need hex. I'll let you write that number down, and then I'll be able to do it too. doing these in my head, so if I got an answer different than you, I probably just simply added it incorrectly. Is that math right? Yeah.
Checking my math.
I also bet. Math is one of those things I do decently alone when I'm in front of a group. Voicemail, you guys are. All right, let's talk about that one, then we'll take a break. How we got there. All right, so first of all, I went through and I did the 1, 2, 4, 8, 16 through 2, just like we've done previously. And I said 512 plus 256 plus 128 plus 8 plus 4 plus 1. So I'm not going to write all this down. That's how I arrived at 909 by adding up 512 plus 56, 128 plus 8 plus 4 plus 1, 909. Now octal, I just divided it into threes again. So I had 101, which was right here, 001, right there, 110, and then just a 1. So again, the implied 421, 421, 421. 4 and 1 is 5, 1 is 1, 4 and 2 is 6, and the 1 is 1, ergo 16, 15. The same thing for hexadecimal. Instead of going in columns of 3s, I went in columns of 4s. Put away a 0 a little bit, but I think we can live with it. So 1, 1, 0, 1, 8 and 4 is 12 plus 1 is 13. And I'm not going to lie, I had to write down A equals 10, 11, 12 to get to the D. So this was D. This was 8. And then 1 and 2, 3. So again, these just became 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, and so forth. So I think we're starting to get the hang of converting a binary number to a decimal, and to a hexadecimal, and to a octal. So we'll take a break. We'll come back about 10 after. Okay, so we took BCA, which is in hex, and we're trying to find binary, we're trying to find octal, and trying to find, not dex, but decimal. Let's write that properly. And basically all we did was we took the A, converted it to binary, 1010, which is 10, 1100, which is 12, and 1011, which is 11. So that gives us BCA. So now that we've got the binary, it's really the same for octal and decimal. Well, really the same for octal as what we did a while ago. So if we divide it into groups of 3, we're going to write 0, 1, 0, 1, 0, 0, 1, 1, 1, and then 1, 0, 1. All right. Yep. Got 3 groups, 4, now we have 4 groups of 3. So 0, 1, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0. Yep, that works out. Okay. Could be me now. So 2, 1, 7, 5. So we've got our binary already. It's right here. We've got our octal. It's 5, 7, 1, 2. And then we've got to get our decimal, and it's just a matter of adding up the digits and changing this to a 1, 2, 4, 8, 16, 32, 64, 128, I'm running out of room, 512, 1,024, 4,096, 8,192. Whee! So I'm gonna let somebody with a calculator do that for me, but we basically are adding up, I'll do the numbers, 8192 plus 1024 plus 512 plus 128 plus 64 plus 8 plus 2.
30.
9930. 9930. So we work backwards. So now let's take an octal and do the same thing that we just did. Everybody got how we did that? If not, we'll go back through it. Going once. Going twice, and sold. Okay. So happy I have my whiteboard back. It's like a long lost friend. All right, let's do 2, 6, 7, 4 octal. And we want binary. We want decimal. We want hex. I'll give you a minute to work through that one independently, and then we'll do it together. So we know that's octal. How many are going to be in each group? 3 for the binary. 3. I'm going to be working on 2. the same thing yet? Or still working? Rework it again, just to make sure, so I'm getting some looks on how do you get that?
Everybody else get 1468?
That's what I got, was 1468.
Anybody else get a
That's the one I got
010 in front
1468?
instead of a 10?
Yeah, that can't be right, 'cause I can tell right now. I think I shifted over, I moved my numbers around a little bit while ago. So let's disregard the decimal from the moment. I'm gonna redo mine, make it right.
I don't like a binary either.
Don't like my binary?
No, show me how you got that 101 in the front instead of 010.
Yeah, cause I got 010.
All right, let's work through this one. Looks like I have done a good job of moving it up. We're gonna go back to 2674, right? Again, I'll do the first and do it all again. All right, 2 is 1, 0. Let me write that a little bigger so I don't have to cram these numbers in. 1, 0. And again, I'm doing in groups of 3, right? So it implies 0, 1, 0. 6 is 0, 1, 1. I mean, 1, 1, 0. So 1, 1, 0. 7 would be 1, 1, 1. And 4 would be 0, 1, 0, 0. So again, go back to our groupings of 3. That goes to here, that goes to here, that goes to here, and that goes to here. So we got binary, so octal to binary at least. So now I'm gonna write my values where I know I screwed up while I go. I'm gonna do 1, 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, and 1,024. So 1,024 and 256 are 1,280, 1,380, 1,388, 1,408, 1,440, 1,456, 1,464, 1,468 decimal. Yay.
So, I got a question.
All right, sure.
Why can't we go all the way to 248 on the, after the, okay, 1024?
We can, there's just nothing there, there's no place. We only have a 1, 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, 1,024. Now, if we wrote a 0 there, that would really be the 2,048 position, but there's just nothing,
Okay,
yeah, there's nothing there.
oh, okay.
So, all right, so we've got binary. There it is. And now hex. It's just a matter of going every 4. So I'm gonna draw that imaginary line. 1, 2, 3, 4. So that's 8 and 4, which is 12, which is what? C. 1 and 2, which is 3 plus 8, that's 11. B. And then the 1 and 4. So at least I did get the hexadecimal equivalent right while ago. So as the old saying goes, even a blind squirrel finds a nut every once in a while.
Squirrel?
Sorry, Kelly. That is triggered right there. So 5 BC, which was a long time ago. We'll do one more just to nail it in. We'll go back to hexadecimal. Because I've always really wanted to know Your hexadecimal number is A, B, C, D. That's hex. So we want binary, octal, and we want decimal. A, B, C, D, hex. I'm gonna make me a cheat sheet so I won't screw up. Doesn't have to go any further than that, though. So, question?
Good grief.
Wee, I made a big number. I ain't gonna math that one in my head. Or what the end result would be. Says my auto was wrong.
You can copy the wrong numbers.
Did I copy?
12571.
All right, so apparently copied the number wrong. Somebody said 1, 2, 3. So it should have been 101. 010 instead of 101 right there, right? Yep. I was a little dyslexic there. Ergo, this becomes a 2. It's a whole lot easier when you kind of see it in a small sheet of record.
There's a reason the first three letters in text does not text.
I still think you're missing this.
Ah. Oh, yeah, I did. I blew it big time. It really is hard to tell. I'm not kidding. All right, let's try this again. All right, 1, 2, 3. That's 1, 0, 1. 1, 0, 0. Right here. And 1, 1, 1. That's right here. And 1, 0, 1. Yeah, I'm missing big time. And then 0, 1, 0. And then a 1. Yay.
Yeah.
Yep, screwed up big time. I should go home to the restroom. So that's 4, 2, 1, and that's a 1. So 5, 1, 7, 5, 2, 1. Is that more better? Yay. My English teacher will be proud. You know how to get the right answer really fast on the internet, huh? Post the wrong answer. If you want somebody to give you the right answer or something, just post the wrong answer. You'll have a million people tell you how wrong you are if you do the right answer. A little old fact. All right, so let's talk about how we got there, how I didn't get there. But first, to get the binary, I just took and broke it up into groups of 4. It's hex. So D, and I wrote me a little chart over here, is equal to 13. So my first group of 4 has got to equal 13. 8 and 4 is 12, plus 1 is 13. C is equal to 12, so 8 and 4 are 12, and nothing here. And I had to get 11 for B, which is 8, 2 and 1, 8, and then I had to get the 10, 8 and 2. So that's how I got my binary equivalent, was just simply taking that hex, grouping it into 4 sections, making the last 4 equal D, which is 13, then 12, then 11, then 10. So boom, got my binary numbers up there. Octal, after many attempts, I had to take those same 4 groupings and put them in 3 groupings. So taking these same numbers, and instead of writing them in 1, 0, 1, 1, I had to go 101, 1, 0, 0, 1, 1, 1, 1, 0, 1, and then 0, 1, 0, and then 1, and then just getting the decimal equivalent of those groupings of 3 to get octal. And of course, decimal, just a matter of going back up here and adding my places under binary 1, 2, 4, 8, 16, 32, 64, all the way out to, holy cow, he gave us a number that had 32,768. So again, just a matter of mathing it through the process. So I think we're starting to get a good handle on this. If not, like I say, we do have some remediation periods out there. And The awareness that really in the long run is gonna be much more important than doing the math, but it really wouldn't hurt you. In fact, one of the things that I took that got me hired at Rockwell, 185 years ago, was they gave us a little test, and it happened to have some octal and some binary and some things like that on it, and I was able to answer some of those questions. Fortunately, I had just went through digital electronics at that time, so it was perfect timing as far as that goes. So you never know when it might come in handy, but mostly having an awareness that we can represent binary in other forms, such as hexadecimal and decimal and octal, will also come in handy, especially when you start looking at PLCs down the line. All right. And again, it's just going back to the fact that in hexadecimal, we group in groups of 4. So we take that string of binary numbers, starting at the rightmost side, group them into 4 subsections, do the 8421, 8421, and go into the next step. And then we get 1Z4. So, and remember, have that little chart, or remember at least that 9 equals 9, 10 equals A, 11 equals B, all the way up to 15, because hexadecimal, which is 16. Hex with decimal, for lack of a better term, hex and meaning 6 and decimal meaning 10, so hexadecimal equals 16. So just like when we talk about the 10 system, we only go through 0 through 9. When we talk about the hexadecimal, we only go through 0 through F. There isn't a number 16 per se, we have to shift columns. All right, so there you go. The binary number 110011111011 converted to its hexadecimal equivalent. First one with the right answer has the right answer.
Hey.
I didn't even group it out for you. So you can narrow one out just by doing the first 4 there. So it's either B or C. And I can do it after doing the second section. Lay it on. Number 2, E7B. That's right. In fact,
You can do the first one on the right side and you get it.
there you go. Exactly. And that's a quiz taking tip there. Just narrowing down what it is. Sometimes it's just as important as understanding what it is, at least as far as taking quizzes. So yeah, we went ahead and did this. 8, there's nothing in 4, so 8, that's 11. So if we convert 11, 9 is 9, 10 is A, 11 is B. The answer has to end with B. There's only one answer that ends with B, and that's the middle one. But if we keep going, 4, 2, and 1 equals 7. 8, 4, and 2 is 13. And if we find the letter of A, it's 10, 11, 12, 13. There we go. So we get E7B.
Shouldn't that be D?
Oh,
It's D. That's what I was thinking when I done it out, I was like, it wasn't right, but that should be a D.
8 plus 4 plus 2, that's 14. I said it wrong, I think. Yeah, it is E. If I said 13, that was my fault. But 8 plus 4 plus 2 would be 14, which is one shy of F, which is 15, which gives us E. And that is another thing, and NIDA is not 100% infallible either. We have some situations where
You will spend too much time arguing with NIDA. You know you're right, NIDA says you're wrong, just go with it.
But question everything, but, understand why you're wrong or why not is wrong. All right, so we used the reverse process. Obviously, we just did a bunch of them. We took F, we converted it to its 4 groupings, which is 8, 4, 2, 1, which gives 15, 9, which is 8 and 1, which is 9, and C, which is 12, which is 8 and 4. So again, using the same groupings, kind of already beat that. All right, what is the decimal equivalent of F9C and the binary number 111110011100? So it goes ahead and groups it. for you in binary. Of course, that really just shows you the grouping, we still gotta do the math. But, if we go along, 1, 2, 4, 8, 16, 32, 64, 128, 6, 5, 12, 1,000, 24, 4,096. So I already know that one, I think. 2,048. So we know the next one's 4,096. So we know these four numbers are getting us, you know, this is basically 1, 2, 4, 8, 16, 32, 64, 128, 2, 6, 5, 12, 1,024, 2,048. Even if we do some rough math, 2,048 plus 1,024 is 3,000, plus 512 is about 3,500. I know that one without finishing it out, simply because we're already greater than 273. There's certainly no way to get to 14,000. But if we add all those up, we should arrive at 3,996, which is the right answer. Again, process of elimination. Practice time. All right, call them out. Convert the octal number 100 to its binary equivalent. 100. So how do we convert it? I'm throwing you a little curveball because it's 100, but it's in octal. So 0, 0, 1, 0, 0, 0, 0, 0. They tried to make your brain think it was a binary number, but it's not. 1, 2, 4, 8, 16, 32, 64. Actually, I just converted it to binary. I'm going to decimal now. So sorry about that. I tried to make it trickier than it was. So the answer is what? C, right? Okay. Convert the hexadecimal. Oh, they're doing it again. Bless their little hearts. The hexadecimal number 100 to its binary equivalent. All right. So what do I write for the first groupings of 4? Yep. Technically 0, 0, 0, 1. That's my first group because it's octal. And then I've got to have my next grouping of 4. I mean, it's that hexadecimal. Then I have my next grouping 0, 0, 0, 0. Then my next grouping. So again, trying to trick our little brains. How dare NIDA do that to us? But if that number had been 215 in hexadecimal, you went, okay. But because it was 100, your first instinct was, oh, that's a binary number. No, it's still an octal, a hexadecimal number. We just got to do it in groups of 4. So I can't really count zeros, but I think it's probably the first one just based on the sheer number. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Yep, this is the first one. Everybody get that? They tricked us. Had that been the number 4, well, let's write. Let's see. I would have been asking for 478. We would have known. We would have still had to have done the binary thing, and we would have had to have done 1, 2, 4, 8. So that would have been that. That would have been that. And it would have been that, and that would have been our binary equivalent. Am I wrong?
0, 0,
8,
1, 0,
4, 2, 1.
1.
Yeah, sorry. It was the first one.
Yeah. 0, 0, 1, 0, 0.
So 0, 0, 0, 1. 0, 1, 1, 1, and then 0, 0, 1, 0. Yeah, I get it.
No.
No.
Am I doing it again?
0, 0, 1, 0.
Yes.
more eights.
No, it's wrong.
I'm glad for it to be on this side instead of this side. Okay, I'm good with that. But you see how easy it is to get mixed up, especially if you don't use these. After a little while, your brain goes, I got this now, and you quit using those little dividers, but when in actuality, you're still needing a little bit of training wheels. And I don't do this every day. I about need training wheels. Anyway. Decimal number 100 to its binary equivalent. So number don't have to go to 128. You have to go to 64. 64 and 32 gives us 96. Nothing under 16, nothing under 8. There we go. All right. So that is 1100100, which is the middle one. So I'm gonna let y'all work the next few as we go. We got about 5 minutes, so we'll do about a minute per. 1011, so it's octal equivalent. Octal. So we got to group by what? Threes.
Three. I'm in three.
Yep. Somebody's already said it. We got a 1 that gives us a 1, and then we got the 011, which gives us 3. 13. Very good. 1011 binary to hexadecimal. B. We've got 8, we've got 2, we got 1, that's 11. A is 10, B is 11. All right, binary 1011 to its decimal equivalent. 11. We've got a 1 in the 8, we've got a 1 in the 2, we've got a 1 in the 1. 8 plus 2 plus 1, 11. AF to binary. If we're taking hex to binary, what have our groupings got to be? 4. Groups of 4. So we need F in its binary form, which is all ones. We need A in its binary form, which is 10, 10. So I see 10, 10, 1, 1 is the 1, 1. There it is. AF. Convert the octal number 77 to its binary equivalent. So groupings are going to be in what? Threes. It's the third one. 3 1s and 3 1s. 4 2 and 1 gives us 7. So it'd be 4 2 1 with a 1 under it. 4 2 1 with a 1 under it. That gives us 77. So basically 6 1s. Convert the decimal number 9 to its binary equivalent. 1001. We got a 1 over the 8, a 1 over the 1, 4 and 2 have nothing. Whoop, there it is. Convert the hexadecimal number. I just want to say hexadecimal or something. I don't know. Hello, she found a lever. Convert the hexadecimal number 16 to its binary equivalent. So it's hex, we've got to do groupings of what? 4. So we've got a 1 definitely in the first one. And then 6 is 0, 1, 1, 0. So the answer is what? B. Second. So again, groupings of 4. 1, 2, 4, which gives us 6. Nothing here. And then a 1, 16. We've done math operations. No, we haven't. So it's break time. we'll, take a break. Come back about 2 or 3 after. We'll try to finish this little section today. Some math. Some math. I know y'all been thinking, we've been doing math. We're gonna do some more math. We'll do some more math. Yes, sir.
Should we have a grade?
No,
Okay.
Fantasy basketball. She does fantasy football. So that's what I try fantasy basketball. I know we would I swear. Did you again? That's a fun night. That's a fun night.
Yeah, this weekend, a couple of us went up to Village River.
That's right.
Yeah, that was a bad.
I had that one here party, Laura, not over to, all the beer pump up.
That sounds like Laura Everett.
And then, say, well, like, now,
Reasons why I tell you to just do binary, and basically just do decimal and be done with it. We've got 61 minus 50, what is that? 11. So if I write 8, 4, 2, 1, 0, oh, excuse me. 1, 0, 1. And there's my answer. And that's way better than this one's complement test. So roll with that. But if you get into a job where your day-to-day adventure is doing this, again, come sit back down with me personally, because one, I want to know what job it is. And two, it really would be a little better. So 1, 0, 1, 1. Oh! How did we miss it? Let's go back and look. All right, so did I math wrong? 32 plus 16 is 48, 56, 61. Oh, one complemented this one. I didn't use the original value. Bad trainer. So that is literally minus 8, that's a 1, 2, 4, 8, 13, right? What's 61 minus 13? 61, 51, 48? 48. So 1, 2, 4, 8, 16. So that may be why our problem answer was wrong. 32. So I've got 1 here, 1 here. There we go. That's what it was a while ago. Yay, we did work it right. Anyway, binary works so much better to decimal. 1, 1. I hate it when I work it right and then work it wrong. 0, 0, 0, 0. Yay. Multiplication, multiply. So let's see how they do it. I've got 101 times 111. 111 is 7. 101 is 5. I know the answer is 35. So I know I'm going to have a 1 followed by a bunch of zeros followed by 1, 1. So let's see what they get. My double noughts here. Oh, it just wants us to go ahead and answer that. Well, I hadn't even taught us multiplication. I was supposed to know that. Let's see if it really works like regular multiplication. Maybe I'm assuming too much. 101, 1, 1, 1. Yeah, this should be pretty easy. We do it the same way. So 1 times 101. Whoop, 101, excuse me. 101, right? So now we put our 0 here. 1 times 101. 1, 0, 1, right? Same way we do math. And then we put a couple of zeros. 1 times 101. Now add it all up. 1 and 1 is 0. 1 and 1 is 0. 1 and 1 is 0, and then 1. So this is 1, 2, 4, 8, 16, 32.
There's two.
32 plus 3 is 35, and we said 7 times 5 is 35. So math works the same. Multiplication math, anyway. So it's 1, 3 zeros, and then 1, 1. And we could have done it either way, right? All right, let's do one more. 1, 1, 1 times 1, 1. 1 times 111, 111. Right, the implied 0. 1 times 111 gives us 1110. 1. 0. That'll be a 1. 1 and 1 is 0. And that's a 1. Everybody understand how I got that? So we did the 1, 1, 1 times the 1, which gives us 1, 1, 1. We place our 0. Do 1, 1, 1. 1 times 1, 1, 1. That gives us 1, 1, 1 with the implied 0. 1 and 0, 1. 1 and 1, 0. 1, 1, and 0, plus 1 more 1 is 1. Carry a 1. 1 and 1 is 0. You carry that 1. So let's see if it works mathematically. 1, 2, 4 equals, well, we need to go up here, don't we? 1, 2, and 4 equals 7. 1 and 2 equals 3, so it should be 21. This is 1, 2, 4, 8, 16. 16 plus 4 is 20 plus 1 is 20. So, just right. So 1, 0, 1, 0, 1. If we click in the box. Okay. Division. Let's let our heads work. All right, it's showing us this: 11 into 111. So subtract 11, and we put a 1. Yeah, that's working just the same. So we write this. That gives us a 1 up here, just as if we were dividing regular math, right? If that were 11 into 1111, our answer would be 101, right? So go to the next step. That leaves us with 0, 0, 1. 11 goes into 11 one time. Actually, 11 goes into 0, 0, 1, none. We bring down the other 1. 11 goes into 11, 101. Same thing here. 10 goes into 1100. Do a 10. Let's do it with a red marker so we can see. We write 10 here. That's a 1, right? That leaves us 1, 0. So 10 goes into 10 one time. That leaves us with 0. That leaves us with a 0. 10 goes into 0 how many times? 110. Yay! Real math, regular math. I like it.
You can do it the same way regular math, take a 0 off.
You could. All right.
Always carries.
Who's ready for a test?
Shut
How
your
about a free
mouth.
test? It doesn't count me for anything. So that's what we'll do. Which number is not a binary number?
Hey.
Hey. All right, before we move, which of those numbers could be a hexadecimal number? Which of those numbers could be hexadecimal numbers? Any of them. That's right. Even 8 could be hexadecimal. Because as long as we see numbers between 0 and F, it could be a hexadecimal. But because we see a 2 in that first one, it can't be binary. How about which of those could be octal numbers? All of them, that's right. Counting on us all to make 100 now. All right, which chart has the correct values in each column for decimal? D, the last one.
D.
This is not even binary. Lord knows what that is. Actually, C and D. No, it isn't D. It's C. What's wrong with D?
It's got
It's got 0. That's the ones column. True. See, NIDA makes tricky questions, not just us. So it is C. Which of those numbers is not an octal number?
B.
Want to hear one loud chime for y'all?
C.
Yeah.
Yep, it's C. A could be decimal, it could be octal, it could be hex, but it can't be binary. B could be binary, it could be octal, it could be decimal, it could be hex. C could be decimal, and it could be hexadecimal, but it can't be octal, because octal doesn't have an 8. And the last one could be any of those other than binary. Very good. Which number is hexadecimal?
No, big a third.
Is.
Okay, yeah, we have G here, which is not there, H is not there, F is, K is not. 1111 is a decimal. Quick. 15. 8 plus 4 plus 2 plus 1, 15. Octal number, 732, the binary. D. Let's talk about why. Octal has to be in groups of 3. So it's 7, because we're talking about 4, 2, 1, 1, 1, 1, and then 30, 0, whoops, I'm writing up here in my 4, 2, 1 position. 4, 2, 1, 0, 1, 1, and then 2, I'm doing it again. 4, 2, 1, 0, 1, 0. That's gotta be the last one, just by the sheer quantity of numbers. Binary number 10111011 to hexadecimal. I got it. It would be B, which is BB. Because if we divide that into 2 groups of 4, you get 1011, 1011, which is a repeating pattern. 1011 is 11. The hexadecimal representation for 11 is B, so BB. All right. Choose your method to subtract the following binary numbers. I'm going to decimal. Y'all want to try one's complement? Feel free. Yep. 16. 19 minus 3. All day long is 16. So if we do have any subtraction or addition problems, binary in one sense is the way to go for subtraction. All right, 101 times 11. they're equivalent. 4, 2, and 1, 4 and 1 is 5, 5 times 3 is 15. A is 15 because it's one shy of flipping over into the 16 place, so 8, 4, 2, and 1 give us 15. Divide the following numbers, 10 and 10, 10. So we can convert, or we can do just 10 and 10 gives us 1. That leaves us, always want to write this on line. That leaves us 1. 10 and 1 goes no times. But 10 and 10 goes 1. Put in D, 101. But again, we could do the math. 8, 4, 2, and 1, that's 10. Divided by 1, 2, that's 5. 1, 2, and 4, 1, 4, 5. So 10 and 10 gives us 101, or 10 divided by 2 in decimal gives us 5, which is 101 in binary. So 101, which is B, then we're going to hold our breath and see if we met 100. If it is, I'm going to give it all to you as a grade, it just won't count. Oh. That was mean, wasn't it? But it was sincere. We want to exit the quiz. Yay, we made 100. This quiz will have some other answers in it, so if you get into NIDA and want to play a little bit, you'll see some of these. If you want to revisit that one's complement and make your head explode, feel free. But again, it's not something you're probably going to see on test. Even if you do, convert it to decimal and just do the math. I want you to understand how this works, and being able to do that is just as important in my mind as the one's complement is. And there's even a two's complement. So if you're having trouble going to sleep tonight, if you'll look up binary and two's complement, I guarantee within 15 minutes you'll feel ready to go to bed. Any questions? All right, so again, for those of you who we have added to NIDA and still can't get in, if you'll stick around, I'll try to help you log in and make sure we're doing that right. For those of you who want to get into NIDA to review this material, hadn't already seen Michelle, to get that in, see Michelle, then come see me, I'll add you in. What are the 2 things NIDA has to have in order for you to log in? Before you even try to log in, let me show you that one more time. Because I'll go over this with my students at the beginning of the semester, and invariably I'll get an email, Mr. Lee, I can't get into NIDA. Are you using Internet Explorer? I was using Chrome. I want to use Chrome. I really want to use Chrome, but I can't with NIDA. So we've got to be in Internet Explorer. For those of you that have Windows 10, this is still a Windows 7 based machine. But if you come down here and type INT, you'll find Internet Explorer, even in Windows 10, it still exists. Edge will be down there, and E for Edge looks just like the E for Internet Explorer, but it's not Internet Explorer, it is Edge. So if you've got Windows 10, and you've got this E icon pinned to your taskbar, that is likely Edge, not Internet Explorer. And even though they're cousins, they don't work the same. It's got to be Explorer. So before I even try to press the login, if I do press the login, I can just close it. I want to go up here to compatibility, and I want to say compatibility view settings. And what would happen is you would see oftc.edu right there. You would have to click add, and then it would pop down here. And now I am truly in compatibility mode for that site. And all that is there are people such as NIDA here who have not upgraded their means and methods for logins and this kind of stuff. And Internet Explorer provides a way to set back compatibility. Now, so do Chrome and Firefox and all those. But again, $5 bounty if you get it to log in under Chrome and Word. Under Chrome or Firefox, I'll give you $5 if you show me how, because I really want to. But it's got to be Internet Explorer for everything else. So any questions, anything we need to review? We've still got a few minutes if you're unclear on something. I see eager faces ready to go home. Y'all want to come back in and start on binary again tomorrow? All right, go.